You know, when you think about what keeps a massive skyscraper standing, you usually picture, like, the giant steel I-beams, right? Or the
Right.
deep concrete foundation.
Right, yeah. We tend to focus entirely on the macro elements.
Exactly. The massive, obvious structures holding up all that weight.
It's entirely human nature, I think, to look at those big load-bearing pillars and just assume they are the only things keeping the whole structure safe from collapse.
But if you look closer, I mean, if the microscopic mortar holding the individual bricks together starts crumbling.
Or if the tiny copper wiring tucked inside the wall suddenly shorts out.
Yes. The whole building eventually comes down anyway. It really doesn't matter how strong those giant steel beams are if the micro components fail. So, welcome to today's deep dive.
Glad to be here.
Our mission today for you, the listener, is to uncover the profound and honestly often hidden physiological impacts of a systemic zinc deficiency.
It's a fascinating topic.
It really is. We are analyzing a huge stack of materials today, spanning from clinical medical reviews and neonatal nutrition theses, all the way to some really cutting-edge microscopic research on intestinal cells and cellular signaling.
And, when you think about grabbing a chalky zinc lozenge at the pharmacy just because you feel a cold coming on.
Right, which is what everyone does.
Exactly. You're really underestimating what this element actually does. The sources make it very clear that zinc is a master trace element.
A master trace element, I like that.
Yeah, it dictates practically everything, from the physical integrity of your gut barrier to incredibly complex cellular communication. We are talking about a master regulator here.
Which is wild.
It is. It's an element foundational for DNA and RNA synthesis,
Yeah.
protein metabolism, and it's the baseline function of your immune system.
So like the actual cells fighting off the infection.
Precisely. Specifically, your macrophages and neutrophils, those are the cells that actively hunt down pathogens. They rely entirely on zinc to function properly.
Okay, well, let's unpack this, because before we can really explore what happens when zinc goes missing from the system, we need to understand how surprisingly competitive your own body is when it comes to absorbing this essential mineral in the first place.
It's a battleground.
Right. My understanding from the reading is that unlike fat or, say, certain vitamins, we can't just stockpile zinc for a rainy day.
No, we really can't. And that is one of the most critical vulnerabilities of human physiology.
Which seems like a massive design flaw, honestly.
You could say that, yeah. Despite being one of the most abundant trace elements in the human body, we have virtually zero capacity to store significant amounts of it in any kind of mobilized reserve.
So we just constantly need more.
Yes, you require a steady daily intake.
Mm.
For children, that requirement's around 3 milligrams a day, and it scales up to about 11 milligrams for adult males, and it's even higher during pregnancy.
So if we have to constantly bring it in, I'm assuming the body has dedicated receptors acting almost like, I don't know, catcher's mitts in the gut to just grab it as it passes by.
Basically, yes. The gastrointestinal tract is the primary entry point, specifically the distal duodenum and the proximal jejunum.
Okay.
And this absorption is meticulously regulated by two families of transporter proteins. You have the ZIP protein.
ZMIP, like ZIP?
Right. They act as the importers drawing zinc into the cells. And then you have the ZNT proteins, which act as the exporters, moving it out of the intestinal cells and into the bloodstream.
But getting into the bloodstream seems to be an all-out turf war.
Oh, absolutely.
Because when we look at the clinical nutrition reviews, the gastrointestinal tract operates a bit like a highly exclusive underground nightclub.
That's actually a great way to look at it.
Right. So zinc is standing outside trying to get in, but the bouncers at the door are these compounds called phytates. And these are heavy in legumes, seeds, whole grains.
And oxalates, too, which you find in spinach and nuts.
Yeah, exactly. So if you eat a diet high in those, they don't just slow zinc down, right? They actively bind to it and just bounce it right out of your system.
The biochemistry of that interaction is brutal for absorption. Phytates have a strong negative charge, and zinc ions are positively charged.
So they just snap together like magnets.
Exactly. They bind together so tightly in the digestive tract that the human body simply doesn't have the enzymes to break them apart.
Wow.
Yeah, the zinc is just trapped and eventually excreted. But, the competition at the door of this nightclub goes beyond just the bouncers. Zinc is also fighting the other guests trying to get inside.
Wait, meaning other minerals?
Yes. Zinc, iron, and copper all share very similar atomic properties.
Okay, so they look the same to the bouncer.
Basically, it means they compete for the exact same absorption pathways in the gut.
Which leads to a massive paradox then. If you take a heavy zinc supplement, or I read even drinking water stored in galvanized containers, which leach heavy amounts of zinc, you can accidentally block your body from absorbing iron and copper.
You can. It happens quite easily.
But on the flip side, treating iron deficiency anemia with a heavy iron supplement can literally precipitate a systemic zinc deficiency.
Right, because the iron just boxes the zinc out of those receptors.
So let me push back on the supplement aisle at the grocery store for a second. If they compete so fiercely, blindly taking a heavy, isolated zinc supplement could actually be doing more harm than good, right?
Blindly over-supplementing disrupts a very delicate zero-sum game of trace mineral homeostasis.
Zero sum. So if one wins, the other loses.
Exactly. If you overload the system with zinc, you box out copper. And copper is essential for maintaining the myelin sheath, which is the protective coating around your nerves.
Oh, wow.
Yeah, so a severe copper deficiency induced by too much zinc can lead to permanent neurological symptoms, numbness, and severe anemia. The balance is incredibly fragile.
Okay, so getting zinc past the bouncers is difficult, and keeping it balanced is this crazy high wire act. And currently, the data shows nearly 2 billion people worldwide are failing to do it.
It's a staggering number.
That's a quarter of the globe suffering from zinc deficiency, and the sources categorize this into two types: acquired and inherited.
Right, and acquired deficiency accounts for the vast majority of those 2 billion people. It stems from malnutrition, heavily phytate-dominant diets like we just talked about, or malabsorption syndromes like Crohn's disease or celiac disease where the gut lining is already damaged.
Makes sense.
But to truly understand the granular microscopic role zinc plays, we really need to look at the inherited version.
Right, acrodermatitis enteropathica.
Yes.
It's a rare autosomal recessive genetic disorder. My read on this from the sources is that it's caused by a mutation in a specific gene, the SLC39A4 gene.
That's correct.
And that gene acts as the blueprint for the ZIP4 transporter, which is the main importer we were just talking about at the nightclub door.
Exactly. So because of a genetic typo, the infant's body simply cannot build the door to let intestinal zinc inside.
Oh, that's terrible. And this typically hits hard about 4 to 6 weeks after they are weaned off breast milk, right?
Yeah. Once that breast milk stops providing a highly bioavailable source of zinc, the infant system just crashes. And the systemic breakdown we observe gives us a terrifyingly clear window into zinc's daily functions.
So what exactly happens?
Well, the clinical literature details severe growth retardation and hypogonadism. But the sensory losses are particularly revealing. Patients experience a complete loss of taste, known as hypogeusia, and a loss of smell.
We should pause on that for a second because it's not just a random symptom, right? The loss of taste happens for a very specific mechanical reason tied to zinc.
It does. Zinc is a structural component of a salivary protein called gustin.
Gustin, right?
Right. And gustin is responsible for the growth and maintenance of your taste buds. So when zinc levels plummet, gustin production just halts.
So your taste buds literally just wither away?
Your taste is essentially atrophy, yes. And the same mechanistic failure happens in the eyes, leading to night blindness.
Wait, night blindness too? From zinc?
Yes. Zinc is required for the function of retinol dehydrogenase. That's the enzyme that converts vitamin A into the active form needed by the retina to see in low light.
So without zinc, the chemical reaction that allows your eyes to process darkness just stops working entirely.
Exactly.
But the most visible and frankly shocking symptom of this systemic meltdown is what happens to the skin. And here's where it gets really interesting for you listening, because the mechanism is crazy.
It really is. You know, the highest concentration of zinc in your skin resides in the epidermis, specifically a middle layer called the stratum spinosum.
Okay.
Within healthy keratinocytes, those are the primary cells that make up your skin. Zinc is constantly working to suppress inflammation. It actively blocks the activation of a pro-inflammatory cytokine called tumor necrosis factor alpha.
This implies zinc isn't just a passive shield sitting on the skin then. It is actively keeping the skin cells from hitting their own self-destruct buttons.
That's exactly what it's doing. Without the stabilizing presence of zinc, those keratinocytes undergo a process of intracellular chelation. The cell essentially realizes it is starving, and it activates an enzyme called caspase 3.
Okay, and what does caspase 3 do?
Think of caspase 3 as a microscopic executioner. Once activated, it initiates apoptosis, which is programmed cell death. The enzyme starts cleaving proteins, fragmenting the cell's own DNA, and tearing the skin cell apart from the inside out.
The cells are literally dissolving themselves.
Yes. The clinical result is called hyperplastic psoriasiform dermatitis.
Which looks like what?
It presents as severe burn-like lesions, particularly around orifices and extremities, and it's accompanied by complete inability for wounds to heal.
Because the cells needed to bridge the gap, keep executing themselves before they can fix the wound.
Exactly.
The irony there is striking. Zinc acts as the biological mortar holding our outer brick wall together. Yet because the body can't store it, our outer armor is on the very first places to visibly crumble away when our absorption fails.
Right. And if the mortar on the outside of the building is crumbling that rapidly, we have to consider what is happening to the internal barriers. The biological mortar we can't see.
Right. As devastating as the skin breakdown is, the microscopic research on the gut barrier reveals a full-blown crisis happening inside the body. Our inner armor breaks down in a way that feels almost counterintuitive when you read it.
It does. So the inner lining of the gut is protected by a thick layer of mucus. This mucus is a physical shield against the digestive acids and the trillions of bacteria in your microbiome.
And it's produced by specialized structures called goblet cells, right?
Yes. And the research we are looking at involves an in vitro study using human HT29-anti-X goblet cells. Basically, they starve them of zinc in a controlled environment to observe their reaction.
And their reaction is total panic.
Complete panic.
Because when these goblet cells sense a zinc-deficient environment, they massively upregulate the expression of their ZIP4 importers. They boost production by like 18 to 25 times. The cells are essentially throwing open every single door and window, desperately trying to grab any trace mineral floating by, while shutting down their exporters, the ZN21 proteins, so they don't lose the tiny amount of zinc they still possess.
It is a cellular state of emergency. And this panic leads to a fascinating physiological failure known as the mucin paradox.
Okay, the mucin paradox. Explain that.
So the main structural components of that protective gut mucus are gel-forming proteins called mucins. The primary one is MUC2.
Got it.
In this panic, the zinc-deficient cells actually increase the mRNA expression for MUC2. They're trying to print more blueprints to build more mucus to protect the gut.
Wait, so the body senses a weakness, prints more blueprints for mucin, but because the zinc is missing, the actual product coming off the assembly line is fundamentally defective. Is that what happens?
That's exactly it. The cellular intention is there, but the manufacturing process fails.
Wow.
The gene expression is high, but the post-translational modification, which is the actual assembly of the protein inside the cell's factory, the Golgi apparatus, is deeply flawed.
Because it doesn't have the zinc.
Right. Mucins rely on a process called O-glycosylation. To form a thick gel, the protein backbone of the mucin needs to be covered in complex, highly branched sugar chains, known as core 1 and core 2 glycans.
And these chains act like sponges, right? Because they are capped with something called sialic acid. I remember that from the paper.
Yes, sialic acid. It holds a strong negative charge, which violently attracts water molecules.
Yeah.
That water binding capacity is what turns a simple protein into a thick, resilient, protective gel.
Okay, so it's like ordering a heavy, waterproof winter coat to survive a blizzard. You sent the order to the factory, the mRNA blueprint is there, but because the factory lacked the right materials, the raw zinc, the machinery malfunctioned.
Yes.
So you get shipped a flimsy windbreaker instead of a parka.
That is a perfect analogy. Without zinc, the specific enzymes inside the Golgi apparatus that build those long sugar chains start to change.
How so?
Well, the expression of an enzyme that halts chain growth increases while the enzymes responsible for branching decrease.
So they just cut the process short.
Exactly. The result is that the factory starts capping those protein chains way too early. Instead of those long, water-binding core 1 and 2 chains, the cells produce severely shortened core 3 glycans.
And what happens to the sialic acid?
The sialation, that crucial water-binding cap, drops by over 70%.
Wow. So the windbreaker isn't just thin, the waterproofing has been completely stripped off.
Precisely. The mucus secreted by these panic cells is structurally compromised. It doesn't form a proper gel, it is flimsy, and it leaves the underlying intestinal epithelium completely exposed to the trillions of bacteria in the microbiome.
Which has to cause massive issues.
It leads to severe inflammation and tissue degeneration. This structural failure explains why severe diarrhea and a heightened susceptibility to dangerous intestinal infections are hallmark, deadly symptoms of systemic zinc deficiency. The inner armor is compromised at a molecular level.
That paints a pretty grim picture of what happens when you lack this one mineral. I mean, we've gone from zinc being the bouncer at the absorption door to the mortar holding our skin cells together to the waterproofing on our internal mucus barrier.
It's highly integrated into everything.
But the analysis of the cellular signaling sources takes it even further. Zinc isn't just a static structural building block. It actually has a dynamic role as a cellular messenger.
Yes, and this really comes into focus when we look at highly specialized, metabolically active tissues, like the mammary gland.
Right?
The mammary gland provides a perfect environment to observe this dynamic role because the metabolic demand for zinc absolutely skyrockets during pregnancy and lactation.
How much does it go up?
It literally doubles.
Oh, cool.
The mother's body has to transfer massive amounts of zinc into the breast milk to support the rapid cell division of the developing infant.
Which brings us back to the transporter proteins we talked about earlier. If a mother has a genetic defect in her zinc secretion into breast milk, like a mutation in the ZNT2 transporter, it can cause transient neonatal zinc deficiency in her breastfed infant.
Yes.
And that is incredibly dangerous for premature infants because they are born with nearly zero zinc stores and they already have sky-high metabolic needs just to survive the first few weeks of life.
Right. The ZNT2 transporter is responsible for packing zinc into the secretory vesicles of the mammary gland, readying it for the milk. If that specific pump is broken, the milk is zinc deficient.
And then the infant rapidly develops the severe symptoms we just discussed.
Exactly, like the executioner enzymes destroying their skin.
Yeah.
But beyond just feeding the infant, the zinc within the mammary tissue itself is acting as an extracellular signaling molecule.
Like a hormone. I mean, I always thought of trace minerals as just sitting inside a cell, being used as an ingredient for something else. But you're saying zinc is actively out there sending messages and giving orders to the surrounding tissue.
It functions very much like a hormone in this context, actually. When zinc is released into the extracellular space, it doesn't just float away. It binds to highly specific zinc-sensing receptors on the surface of neighboring cells,
Like which ones?
most notably a receptor called GPR39.
Okay, so when a zinc ion plugs into the GPR39 receptor on the outside of a cell, what happens inside?
It sets off a massive intracellular cascade. It triggers an immediate release of intracellular calcium, and it activates these pathways known as ERKs.
ERKs.
Yeah, ERKs. These are essentially the cell's internal communication lines. Activating this cascade drives cell migration, proliferation, and tissue repair. The zinc is actively instructing the tissue on how to grow, when to divide, and how to repair damage.
Which means zinc isn't just a brick in the wall. It is the foreman yelling instructions on the construction site.
That's a great way to put it.
So it is actively regulating healthy cell growth versus malignant mutations. And that brings us to a very heavy implication in the research regarding breast cancer.
Right, because zinc is deeply involved in regulating both cell growth and apoptosis. The programmed cell death we mentioned earlier, a severe imbalance in how zinc is transported and stored inside the cell, is intimately linked to epithelial malignancies.
The sources mentioned a specific link there.
They do. The research demonstrates that in breast cancer, there was a subtype-specific accumulation of intracellular zinc pools.
Wait, are you saying that cancer cells are intentionally hoarding the zinc?
They are essentially hijacking the plumbing. Malignant cells alter the behavior of those ZIP and ZNT transporters we discussed. They pull zinc into specific compartments of the cell to block apoptosis.
So they use the zinc to survive.
Exactly. They use the zinc to prevent the cell from dying when the immune system tells it to die, driving the malignant phenotype forward. The zinc is no longer repairing the healthy tissue. It's being weaponized by the malignancy to fuel uncontrolled immortal growth.
To realize how much power is packed into such a tiny trace element, it changes your entire perspective on nutrition. I mean, we started this deep dive talking about a little lozenge you take when you have the sniffles, but we've uncovered an entire hidden universe of physiological architecture.
It's profound. Synthesizing this entire journey reveals a stunning, highly interconnected biological cascade.
So what does this all mean for you listening?
Well, a systemic lack of zinc is far more than general fatigue. It starts as a desperate losing battle for absorption in the duodenum against compounds like phytates.
The bouncers.
Right, the bouncers.
Yeah.
And when the body loses that battle, it initiates the molecular failure of the mortar holding our skin together. It leads to the structural enzymatic collapse of the protective mucus inside our gut. And it cascades all the way down to defective cellular signaling, leaving our immune system totally vulnerable and our cellular repair mechanisms susceptible to malignant hijacking.
It is the ultimate microscopic butterfly effect happening inside your own tissues. Which brings me back to that crumbling building from the beginning of our deep dive. Given that the human body is entirely incapable of storing this master mineral and knowing that even a mild deficiency fundamentally alters how our cells build their protective barriers, I want to leave you with a thought to mull over that extends beyond our own biology.
Okay.
Current environmental research shows that rising atmospheric CO2 levels are mathematically proven to reduce the zinc concentration in staple crops like wheat and rice globally.
That's concerning.
It's terrifying. The very plants we rely on are losing their ability to pull this element from the soil. So, as our environment changes and our crops become less nutritious, are we unknowingly accelerating a hidden global deficiency?
It's a very real possibility.
The next time you experience an unexplained bout of brain fog, a minor stomach bug that you just can't shake, or a paper cut that refuses to heal, you have to wonder, is your body's macrostructure failing? Or are you simply a few milligrams short of the microscopic mortar you need to keep your physiological armor intact?